Welcome to the NPTEL course on Scalable Data Science, lecture number 3. Today's lecture is on background on linear algebra, which will be needed for the course. I am Professor Saurangshu Bhattacharya of Department of Computer Science and Engineering, IIT Kharagpur. In this lecture, we will recall the concepts that we need in this class. We will especially go into the geometric intuition for linear algebra. We will outline some basic concepts, and then we will discuss linear transformations and vector spaces. Then we will discuss properties of linear systems. Then we will discuss eigenvalues and eigenvectors of matrices, and finally, we will briefly discuss singular value decomposition. A vector in Rn is an ordered set of n real numbers. So, for example, this is a vector in R4 and this is a column vector. This is a row vector again in R to the power 4. M by n matrix is an object with n rows and m rows and n columns. So, this particular matrix is a 3 by 3 matrix. Now, transpose of a vector or a matrix is a reflection of the vector or the matrix along the diagonal line, which is this particular line of the matrix. For example, the matrix AB transpose, the column matrix AB transpose or the column vector AB transpose becomes the row vector AB, whereas the column the matrix ABCD transpose becomes the matrix ACBD. Okay. We note that we can have a matrix vector product which is AX, the transpose of which becomes X transpose A transpose. Also note the definition for the vector norms. The LP norm of a vector V with components V1 till Vk is denoted by summation over I mod of Vi to the power p whole raised to the power 1 by p. We will commonly use the L1 and the L2 norms. The L infinity norm of a matrix is the max over all the components, the absolute value of all the components of a vector. Also note that the length of a vector V is the L2 norm of the particular vector. Next, we go into the dot products. First, we define the dot product between two vectors u and v with components u1, u2 and v1, v2 as sum over u1 v1 plus u2 v2. So, in general, if you have a vector u with components ui and another vector v with components vi, then u dot v is equal to sum over I ui times vi. Going forward, we can also define the matrix product as given in this example. So, if a matrix A has A11, A12, A21 and A22 and similarly the matrix B, then the entries of the matrix AB are of this form. A11 times B11 plus A12 times B12 and so on and so forth. In other words, the product, the entries of the matrix A times B are, so the ijth entry is the ith row of a matrix times jth column of the matrix B. Okay. We can also define the dot product of two matrices. We can represent the two vectors in terms of column matrices or column vectors, and then we can represent the dot product of two vectors u and v in terms of the matrix product u transpose v, which is the same. Similarly, we can define the outer product between two vectors as given here. There are some special matrices which we will come across in our discussions. The first one is the diagonal matrix, which is given here. As you can see, only the entries on the diagonal have values, all the off diagonal entries are 0. Similarly, we can define an upper triangular and a lower triangular matrix. In the upper triangular matrix, only the entries upwards of the diagonal are non-zero, all the entries below the diagonal are non-zero, and vice versa. Another important matrix is the identity matrix, which is just the matrix of all 0 entries and ones only in the diagonal positions. Next, we discuss matrices as linear transformations. The first transformation that we discuss is the scaling transformation. You see that the matrix A here transforms this vector 1 1, which is a vector like this, as 5 5, which is just a scaled version of the original vector. Hence, this transformation is called the scaling transformation. Next, we discuss the rotation transformation. Note that the matrix 0 minus 1 1 0 rotates this vector. So, when matrices when multiplied with this vector 1 1 produces the vector minus 1 1. This is the vector 1 1 and this is the vector minus 1 1. Note that the length of both the vectors are same. However, this vector has been rotated by 90 degrees. So, this matrix is called a rotation matrix. Similarly, we can define a reflection matrix which takes the vector 1 0, and transforms it to the vector 0 1. In other words, it is performing a reflection about the line, about the 45 degree line. Another matrix is the projection matrix, which takes, for example, this vector 1 1 and projects it onto the x axis. Note that there is a 1 in the first entry and all the other entries are 0. Such a matrix would take any vector and project it onto the first dimension. Next, we describe an important concept of vector spaces. Formally, vector spaces are a set of vectors which are closed under addition and multiplication by real numbers. This is also sometimes called a linear combination of the vectors. So, for example, here we have shown that the vector x is a linear combination of vectors v1 till vn, with where v1 till vn are vectors and alpha 1 till alpha n are the corresponding real numbers which they are multiplied by. Closure means that any element in this set can be generated as a linear combination of elements, other elements in the set. A subspace is a subset of a vector space which is a vector space in itself. For example, you can see here that these coordinate axes denote the 3-dimensional vector space. So, for example, if you take the vectors 1 0 0, 0 1 0 and 0 0 1 as the maybe I will make it 0 1 0 and so if we take the vector 1 0 0, 0 1 0 and 0 0 1, this can generate all the vectors in R3. A linear combination of these 3 vectors can generate all the vectors in R3. However, if we set Z3 equal to 0, then this and this are sufficient to generate this subspace for which Z equals 0. We can also extend the notion of planes to n dimensional subspaces using hyperplanes, which we will discuss next. This is a linear equation. So, matrix equations or systems of linear equations can also encode a set of linear constraints. So, for example, the first equation encodes a linear constraint which is denoted by this hyperplane, okay, and the second one encodes another linear constraint which is denoted by the second hyperplane. Okay. Together they can be written as a system of linear equations in matrix notation as given below. Now, a system of linear equations can be generally written or compactly written in matrix notation as Ax equals B, where A is the coefficient matrix, which is in this case this matrix, x is a column vector and B is another column vector. If we want to solve this system of equation Ax equals B in terms of x, it is solvable only if the vector B can be written as a linear combination of columns of A. So, for example, in this case the columns of A matrix are 1 2 1 and 0 3 3. So, only those vectors which can be written in this form for u times 1 to 1 plus v times 0 3 3 equals b, they form the subspace given by this hyperplane. The set of all possible vectors generated by a linear combination of columns of a matrix is called the column space of the matrix A. Another important concept is the null space of a matrix A. The null space of a matrix A is all those vectors which are solutions of equation A x equals 0 or A x equals 0 vector. So, for example, 0 0 is a part of null space, is always a part of null space, or the origin is always a part of null space, because any vector multiplied by 0 will give 0. You can check that for this coefficient matrix, all vectors of the form C, C and minus C will actually generate the 0 vector. Hence, this set of all vectors of this form C, C and minus C, where C can vary, C can be any number, constitute the null space of this particular matrix. Next, we discuss the concept of linear independence. A set of vectors v1 through vk are linearly independent if a linear combination of these vectors equals to 0 implies that the coefficients are all 0. In other words, a set of vectors are linearly independent if their null space is the origin. Note that the origin is always contained in the null space. If all vectors in a vector space can be expressed as linear combination of a set of vectors, say v1 to vk, then the vectors v1 to vk are said to span the entire vector space. So, as discussed, these three vectors span the entire vector space of R3. Similarly, you can see that this and this vector together also span the vector space of R3, and any vector can be generated as a linear, for example, the vector 2 2 2 in this case can be generated as a linear combination of this vector. A basis of a vector space is a set of linearly independent vectors which span the vector space. The dimension of a vector space is the number of degrees of freedom of a vector space, or it is the maximal set of linearly independent vectors which can generate the vector space, or alternately it is the minimal set of spanning vectors of the vector space. These two are equivalent. So, the vector space R3 has dimension 3, as we know that 3 vectors are sufficient to generate all the points in R 3 and more than 3 vectors are not necessary, and rather less than 3 vectors are not sufficient to generate all the points in R 3. Next, we discuss the concept of rank of a vector space, rank of a matrix. Sorry, the rank of a matrix is the dimension of the column space of the matrix. For example, this matrix has a rank 2 because it has the dimension of the space generated by its columns is 2. In this case, note that it also has 2 columns and both the columns are linearly independent. You may note that this is also equal to the dimension of the row space. So, for example, in this case, even though there are 3 rows, you can check that one of the rows can be generated by a linear combination of the other 2 rows. For example, 1 and 3 can be generated as a linear combination of 2 and 3 in this manner. Next, we discuss an important result in linear algebra, which is also called the fundamental theorem of linear algebra, which is given a matrix A, let us say it is an m by n matrix with rank R, column space of A has dimension R. This is coming from the definition of rank, which says the rank of a matrix is the dimension of the column space of a matrix. Also, the null space of A or the null space of A transpose has dimension n minus R, which is also sometimes called the nullity of A. Okay. Hence, and also since the dimension of the row space and the dimension of the column space are same, hence the dimension of the row space, or which is also the dimension of the column space of A transpose, is also R. Hence, the important result that given an n dimensional space, the rank plus nullity of the matrix A is equal to n. Next, we discuss the concept of inverse of a matrix. In order to solve the system of linear equations A x times b A times x equals b, we can write a closed form solution if we can compute a matrix called A inverse, which has the property that A times A inverse equals A inverse times A equals identity. Then we can simply write x as A inverse times b. We can verify that this is indeed true because you can write identity here. So, you can write x as A x and then you can write the identity as A inverse A, and then you can write A x as b. The matrix A is called non-singular matrix if and only if such a matrix A inverse exists, and if that happens, the system of linear equations A x equals b has a unique solution. Some special definitions: a matrix A is called symmetric if A equals A transpose. Furthermore, a matrix A is called positive definite if for any vector x, x transpose A x is greater than 0, and if the inequality is not strict, then it is called positive semi definite. So, let us see a common positive semi definite matrix, which is the identity matrix. Note that if we have any vector a b c, then if we call this vector as x, then x transpose A x is nothing but a square plus b square plus c square, which is positive for all values of a, b and c, hence all vectors x. Hence, this matrix is positive semi definite, whereas this matrix is not necessarily a positive semi definite matrix. Okay. A very useful fact is any matrix of the form A transpose A is always positive semi definite, because you can write x transpose A transpose A x as A x transpose A x, which is nothing but the norm of A x, or rather norm of A x squared, L2 norm of A x squared. We also discussed the notion of determinants. Determinants are numbers which are calculated from a matrix. For a 2 by 2 matrix of with entries A, B, C, D, the determinant value is given by A D times B C, A D minus B C, sorry, and for a 3 cross 3 matrix, the determinant is given by, is computed recursively as A11 times determinant of this submatrix minus A12 times determinant of the submatrix formed by taking these two rows, and plus A13 times the determinant of this submatrix. For higher order matrices, the determinant can be defined similarly. An important thing to note is that if a matrix A is singular or rank deficient, if and only if its determinant is 0. If its determinant is not 0, then the matrix is invertible. Next, we discuss the important concept of eigenvalues and eigenvectors. So, the question comes, how can we characterize a set of matrices? One way to characterize a set of matrices is to find solutions of equation of this form A x equals lambda x for all x. Okay. So, all pairs of, here note here that here lambda is a value and x is a vector. So, lambda is a number and x is a vector. Okay. So, of course, if x is equal to 0 and lambda is equal to 0, this equation is trivially satisfied. So, we are seeking solutions which are non-zero or where x is both x and lambda are non-zero. Okay. One way to solve this is to look for solutions to this linear system of equations, which is possible only if the determinant of this coefficient matrix is 0. Okay. Using this concept, we can solve the eigenvalue problem. For example, given this particular matrix, we can compute, or given this matrix A, we can compute the matrix A minus lambda I, and then we can compute the determinant of this matrix, which in this case turns out to be this particular number. In general, we will have a polynomial in lambda. We can solve this equal to 0 to get the degree of the polynomial times values, and in case of a n cross n matrix, this turns out to be n. The degree of this polynomial, or which is also called the characteristic polynomial, turns out to be n. By solving this, we can get the lambda, after which we can solve for x. Now, the significance of eigenvalues and eigenvectors is that the eigenvalues and eigenvectors scale the eigenvectors are the directions in which any vector, when transformed by this matrix A, is just rescaled or scaled by the eigenvalue. This is because, as you can see, for the eigenvector direction, let us say x, your Ax becomes nothing but a value lambda times x. This is the interpretation which is shown here. So, for example, in this case, this matrix scales any vector in this direction as in this direction by 1 and any vector in this direction by 2. Okay. Hence, this is an eigenvector and this is another eigenvector, and the corresponding eigenvalue for this eigenvector is 2, whereas the corresponding eigenvalue for this eigenvector is 1. Now, eigenvalues and eigenvectors have very interesting properties. So, the first property is, if lambda 1 till lambda n are distinct eigenvalues of a matrix, then the corresponding eigenvectors E1 till En are linearly independent. Next, if E1 is an eigenvector of a matrix with corresponding eigenvalue n, then any non-zero scalar multiple of E1 is also an eigenvector with eigenvalue lambda 1. This is very clear because you can check that A of, let us say, alpha times x is also equals lambda of alpha times x. The third property is also very useful. Any real symmetric square matrix has real eigenvalue with orthogonal eigenvectors, which can also be chosen to be orthonormal. So, in other words, your set of eigenvectors forms a orthonormal matrix and the set of eigenvalues are real and symmetric. In fact, if you calculate all the eigenvectors, you can write the matrix A as a matrix of eigenvectors u times lambda times u transpose. So, this is also called the eigenvalue decomposition of a matrix, and where u is the matrix of all eigenvectors and lambda is the diagonal matrix of all eigenvalues. Extending this is another concept called the singular value decomposition. So, given any matrix A which is an m cross n matrix, it can be written as a product of three matrices U, which is an m cross m orthogonal matrix or orthonormal matrix, D, which is an m cross n diagonal matrix with, so this is the matrix U, which is an m cross m orthogonal matrix or orthonormal matrix. The matrix D is a m cross n diagonal matrix. So, in this case, let us say if m is greater than n, so it will only have n many diagonal values, rest all the values will be 0, and V, which is another n cross n orthonormal matrix. This decomposition or this way of writing a matrix A is called the singular value decomposition. The singular value decomposition has some very important properties or important and useful properties. So, for example, the rank of a matrix A is equal to the number of non-zero singular values of the matrix A. So, every matrix may not have eigenvalue decomposition in real numbers, but every matrix will have a singular value decomposition, and once you calculate the singular value decomposition, the number of non-zero singular value determines the rank of a matrix. For a square matrix A, you can see that it will have for a n cross n square matrix A, it will have sigma 1 till sigma n many singular values, and it will be non singular only if none of the singular values sigma 1 till sigma n is 0. In other words, the matrix will be singular if at least one of the singular values sigma 1 till sigma n is 0. So, with this we come to an end of this introduction to linear algebra. The reference for this, a good reference for this is the Introduction to Linear Algebra book by Gilbert Strang, and another very nice reference is the Wikipedia.